Okay, welcome to section 4 of chapter 20, which is the start of particle physics. Now, particle physics is a fundamental science. Okay, it's the fundamental research of how particles behave. It has grown out of several other areas and it links to every other area because all particles must behave in this way. Sometimes called high energy physics, it's starting to look at the behaviours of stuff that are working at more of the extremes. So the whole of astrophysics and cosmology is based on the work of particle physics, so there's a lot of crossover, etc, etc. So loads of big areas. It is not radioactivity. It has come from radioactivity. It developed after the research of radioactivity. And it's all based around the kind of the chemical structure, shall we say, the particle structure of everything in physics. So this effectively is our periodic table. This is where we're at the moment, our periodic table of, let's get rid of reflection a second, sometimes known as the standard model, or usually known as standard model. And it brings us different groups, different types of particles. Okay, so we have 3 groups here. They're doing different things, so these will link into why these are the cause of things happening in quantum mechanics, and these are the actual physical particles of matter. We don't experience most of them because our energy is too low, but if you increase the energy, you can make the less stable particles. So the most stable particles are our first group here: protons, neutrons, electrons, and neutrinos, which we'll come back to in a second. And it all links into things that are still being researched now, some only just discovered or proven as such. So the Higgs boson or Higgs field is what all of these create, okay, or what all of these rely on. So lots and lots of theoretical stuff. Because of that, it's quite factual, but this start is really kind of the introduction of big ideas. So section 4. And as I said right at the beginning here, a lot of the original research was done by people like Rutherford, excuse me, and Marie Curie, and all of those people at that time, doing work with radioactive substances. We have people like Anderson, the Americans, who are doing work on cosmic rays, so a lot of work in the mountains, looking at what literally shot out of the sky, and then kind of combining the two together. Starting to create accelerators, so rather than waiting for cosmic rays, we could control them. So accelerator physics is where we are now, although that's kind of more to do with the actual machines. We're going to look at the ideas behind the research, and it's all in the end about energy, okay, going deeper and deeper into substances. Okay, so in the first 2 sections, or section 2 and 3, we realised, Rutherford was realising around about 1900 that atoms aren't solid. J.J. Thomson had already done that. There was particles, discovered the first subatomic particle, the electron, and things were pretty concrete. We were finding things as though there were layers inside an onion, but it's about this time that a lot of the work that comes through particle physics started being noticed, and it's all implicit, it's all theoretical, it's looking at things and realising there's something missing and so on. So the first hint followed quite rapidly on from the alpha particles. So Rutherford was using alpha particles as a research tool with his gold leaf scattering experiment, and other people were noticing other things. Now, alpha particles all have a very distinct energy. They have a certain amount of energy. They'll come out at a certain speed from the nucleus when it decays. Beta particles, completely different. Some were fast, some were slow, some were penetrating through things, some were not. And if there is a certain amount of energy being released, which was the hypothesis, by the splitting of an atom, then those nuclei, if they're all the same nuclei, should give out the same amount of energy. But when we study the different the energies, the kinetic energies of different beta particles, what we found was there was a majority. There was some had 0, only just were barely moving, and there was a definite maximum. And the maximum was that one that should have been given out. But why were they not all coming out at that same velocity? Alpha particles, whatever their value would be, would come out as a spike. Whereas there we've got a big distribution, we've got a whole range of different energies. So it's Wolfgang Pauli who came up with various other things as well, but he hypothesized that there were these ghost-like particles, and they were very small, they're very difficult to detect, because otherwise you would have picked them up with cloud chambers and Geiger counters and things like that. So really hard to detect. They must be neutral because the mathematics of charge still worked, and because they were really small, instead of neutrons, which we already had as a theory, he came up with something smaller. So from bambino for Italian, neutrino was a neutral smaller than small particle. And it was this that really was the first evidence for particles that were not, shall we say, normal, the main ones that we think about every day, protons, neutrons, and electrons. However, it's actually a mathematician, so again it was theorists who came up with this first. Paul Dirac, using derivations around about research on particles and charge and so on, but in a very maths-based way, was really just came up with theory, and he had 4 solutions to a conclusion, so rather like 2 solutions from a quadratic, could be plus or could be minus, and he ignored 2 of them. Okay, he didn't try to explain it, but actually what his mathematics has shown is that particles, these electrons, will have an exact but opposite equal particle. Okay, so he discovered the positive electron, which is nowadays shortened to positron. Okay, so just be wary with the language. Positron, not proton, not photon, etc., etc. So you can see people get mixed up, so just be careful. So positron, electron, they go together. And basically, we have since found from then, and again Wolfgang Pauli did a lot of work on this, and Enrico Fermi, they realised that actually every particle that we know of has a particle, must have its own antiparticle, antimatter particle, matching it in every single way but with opposite charge. Now we're going to get deeper into this because there are different types of charge, not different polarities. So there's electrical charge, positive and negative. We've also got other types of charge, so we'll introduce that because that comes into our periodic table, our standard model. Okay, but it was Anderson who first noted that, and I'll show you the photo, very famous photo in research, high up a mountain in the not Mount Whitney, which were a lot of research in California, but actually out in Pic du Midi, down in the Pyrenees. Research centre there, high up, near the clouds, near to space, therefore lots more positive particles coming from space. However, this is a particle that shot up through the Earth and then created basically this antimatter particle. Okay, so it was his who first took a photograph of a positron, a positive electron. Okay, so crucial bit is they have certain numbers that represent all these charges. The maths is checking that these are balanced, so in chemistry you're used to balancing the electric charge and obviously the number of particles. Here we have a little bit more complicated. They can all change, they don't split apart and rejoin like in chemistry. We can actually change the particles. But again, it's all about checking they add up. Okay, and what are they made from? There's a layer in beneath that we'll go into as well, which is looking at quarks. So, crucial bits. There are 2 phrases you need to know your way around, and it's one of those that in the last version of OCR you had to be able to spell right. One was pair creation, or pair production, fairly straightforward, and the other one is annihilation. Okay, and this is the kind of the crux of everything you see in all those photos, those images of particles being made in various particle accelerators and other research. Okay, and the principle was happening all the time. We think this is happening at the edge of black holes, where things are moving really fast because of the gravitational field, and therefore you have a natural particle accelerator, things like that. So the whole host where they appear. But annihilation and pair creation are kind of the opposite of each other. So this is probably the easy one to get your head around first. we don't normally see things like antiparticles. We don't normally see positrons. Why? Because if they get anywhere near an electron, i.e. their opposite partner, they'll completely disappear in a burst of energy. Okay, they will, it's not vaporized, they won't disappear, they won't change state, they will just disappear completely. They will not be there, but all the properties that they have to cancel out, and that's why you can only annihilate the matching particles. So a positron can annihilate an electron and vice versa, and a proton can annihilate an antiproton, but it can't annihilate a positron. They have to be the same pairs. Okay, so pairs of particles. Does it happen? Well, yeah, it does. It happens a lot, but again, only if you've got high energy, so not really on Earth so much. But when they do, well, where does that energy go? The only thing that we have, there's no physical particle to push, so when we're talking about work done, it's not doing work, there's no forces involved, it's just releasing pure energy. So it gives out photons of light. Okay, now here's a diagrammatic purpose. Two particles coming together, they're attracting because they're positive and negative, they're opposite charges, and they're coming together, and when they meet, they annihilate, burst of energy, and the energy comes out as photons. Now realistically, they're going to come together, and what happens is back-to-back photons disappear out. It's got to do with momentum and things like that. Okay, so you are always going to transfer our two particles into two photons of energy. Okay, how much energy? Well, this is where Einstein came in. Okay, so this is where he started coming in with his ideas from special theory of relativity and the most famous equation that we know of, m times c squared. So theory behind it, it's all to do with light and so on. However, in terms of what we're saying here, this is just a large number, 3 times 10 to the 8, which when you square it is 9 times 10 to the 16. So a big amount of energy can be created from a little mass, or little masses can be created from a large amount of energy. They are, crucially, two sides of the same coin. So really, when we talk about particles, we shouldn't talk about their mass and what energy they have. We actually need to talk about their mass energy. Okay, it's the same thing. So mass can be converted into energy, energy can be converted into mass. Very easy to do using E equals mc squared. Now if we were to take an example and look at U, for example, then that's a lot of energy. Okay, if you think of 1 kilogram, well again that's 1 kilogram times 9 times 10 to the 15 joules that would turn into. So, you know, 1,000 million joules. Yeah, 1,000 gigajoules. Sorry, 1,000 terajoules rather. So that will be enough for 1 kilogram to be annihilated to basically run the world, all the resources in the world for a long time, you know, getting on for a year. That's a lot of energy if we can make a kilogram disappear with a kilogram. When we're looking at examples of this, well, we have seen this nuclear energy, the energy due to its mass being released in nuclear bombs and atomic bombs. So testing radioactive bombs, you're changing this. Our sun is going through this process. It's actually annihilating and creating particles all the time, depending which way they are changing them, and it's creating the energy it's given out from the sun every second is because it's losing mass every second. Okay, so that's how it's going on about. So little analogies here to help you, but the crucial thing, the law of conservation of energy, is actually law of conservation of mass energy. So you need energy just to exist, you need extra energy to move and exist. Okay, so if we want the absolute amount of energy rather than the changes of energy, we need to consider all forms of energy, including the energy to create matter or to create mass. Okay, so this is the rest mass energy, and I just point out in some examples they'll often use a little 0 to kind of say that's your main value, okay, your original value. So let's jump into kind of ideas behind it. Well, it just means that we can think of things in different ways. So protons, we know they have a rest mass of 1.673 times 10 to the minus 27. If you multiply that by the amount of c squared, we end up with, and you can put this all through, check it, 151 picojoules. Okay, now I shouldn't do that because of that there, so I'm going to do it underneath. Roughly, again, to three significant figures, the neutron's the same, so 151 times 10 to the minus 12. Okay, so that's a little bit of energy. If we are looking at electrons, they have a lot less mass than those, they're going to have a lot less than that. And that approximates to 82 times 10 to the minus 15 joules. So 82 femtojoules. Okay, really, really small. Now, not very convenient units, so we'll look at more convenient units rather than joules, because joule on the scale of a proton is pretty big. Okay, it's a huge amount of energy. For us, 1 joule's not a lot. Lifting an apple up 1 meter, well, how many protons is that? Yeah, so that gives you the idea of scale. So we will use a more convenient unit rather than joules in a second, but let's just drive onto the key points. Okay, we have the antiparticles themselves. Often we won't bother, strange enough as you can see, writing antiproton. What we'll just do is a symbol, and the symbol, lowercase p for proton, with a bar on the top. Okay, that's not average. We'll often say p bar in particle physics. And neutron, again, n bar. Okay, now sometimes we will conveniently add things like charge, so plus or minus or 0, but we'll leave that for the moment. Okay, the anti-neutron, and the crucial bit with the electron is because it was found earlier, it came up with its own name, so positron, which makes it a lot more convenient when you're doing this in the exams. So E bar, sometimes written as E plus, which is more convenient. Okay, again in the exam you tend to have shorter questions on these. Just put the bar over for the antiparticle. Now, how does it work? It's just the opposite property. So antiproton is negative, and again it's 1.6 times 10 to the minus 19. So it must have the exact same amount of charge, because if that meets that, then the energy left over can't be charged, so the charge has to cancel out. Okay, it's just the mass being converted to energy. And again, it shares the same, it's still matter. Okay, antimatter has still got mass and everything else, but it is that it's going to have that same value of mass as its particle. So all of its properties apart from mass energy, okay, rest mass energy, are the opposite. The rest mass energy is exactly the same. So again, 151 times 10 to the minus 12. Now, you may think anti-neutron, or if it's neutral and it's the same mass, then surely it's the same particle. But no, and we'll show you why. You have to go deeper into the structure to realise that. So, positron is positive electron, 1.6 times 10 to the minus 19. Okay, but again, mass is the same, so 82 times 10 to the minus 15 kilograms, joules, rather. Now, annihilation means that the mass can't cancel out the mass, therefore we're going to end up with twice that mass, and then it's converted into energy, E equals mc squared. So we've got that conversion going on here. The charges would cancel out. However, we can create pairs of particles. Okay, it has to be a pair. We can't create a mixed match like an antiproton and an electron. We have to be able to create pairs. And that pair production or pair creation, both are perfectly fine, can happen and does happen all the time. It fits in with the theories and observations that we've taken from some of the black holes. Hawking radiation is part of this, for example. But it's all about having enough energy to make the particles. Okay, so what happens normally is our energy, our photon, our HF, comes in and its energy is absorbed. Now, we did this last year where an atom absorbs a photon and it excites the photon, excites the electrons in it, but not enough for them to escape usually, and they fall back down. Some materials, some metals, if it's UV frequencies, it's enough energy for the electron to escape. Okay, those are really low levels of energy. Those are killer electron volts. Okay, so in terms of scale, much smaller. But if we have enough energy, if we are going much higher in frequency, then that energy doesn't actually change the atom itself. It's just that energy has to disappear into something. That energy is absorbed. It's far too big for it. It's effectively a flashbang and a wallop, and it's enough to create your pair of particles. E.g., there's your electron bar, and there's your electron. Okay, so that's your examples. Or proton and antiproton. Again, negative, positive. So again, you have to create a pair, because otherwise you are not conserving properties. You'd have charge suddenly appearing, you'd have mass suddenly appearing, things like that. Other properties, other charges exist. So you always have to create two, hence pair production. Okay, but the energy of this will be different from the energy in the previous one. Okay, so if we just think of the two, let me just move them into the same view, there we go. Two particles of a certain amount of mass, certain amount of mass on our previous table, changes into a certain amount of energy. Okay, so 82 if it's, let's say, a photon and an antiphoton, positron and an anti, the bottom row, electron and an anti-electron, electron and a positron. If they annihilate, then that much energy appears here for each of them. So your two photons will share 164 femtojoules of energy. Okay, in other words, the energy of one goes into one. So two come in, two go out, fairly straightforward. Here, only one photon to create that 164 femtojoules. Okay, so this one has to actually have twice as much energy before it hits or gets close to an atom. And so therefore your frequency has to be twice as high as these. Okay, just simple maths. Energy in, energy out. Okay, and that's always the golden rule of conservation of energy, or in this case, mass energy. So this is energy due to mass, this is energy of the photons. Okay, so where do we go with that? Well, the maths of it is nice and easy. If this has higher energy, then just like photoelectric effect, it's enough to, in this case, not release electrons, but actually create a pair of electrons or protons or other particles. And so any spare energy is given to these for them to escape. It's given as kinetic energy. Okay, so we've got what seems like quite a complicated picture, but again, it is the same principles as photoelectric effect. Okay, so if two particles need 10 megaelectron volts to be made, and the photon has 16 megaelectron volts, again, notice convenient numbers, much easier, then basically you're going to create it and the rest comes in. So just to give you an idea, EH equals mc squared, 2 lots, okay, because it makes two particles from our one energy in, plus 2 times kinetic. Okay, and again, these are usually made symmetrically, so they will share the same amount of energy left over. So for example, using this one here, if you've got 16 MeVs, that's going to turn into enough to make your particles with 6 left over. In other words, each particle created has 3 mega electron volts. Okay, and that's the idea. So, by giving particles lots of energy in different ways, perhaps using photons or not, again, I should point out that the frequencies to get these kind of energies, they're all gamma rays. Okay, it's not about ultraviolet here. This is way higher energy to make this all happen. But it does give us that stuff that we discussed in the magnetic topic as well. So here, as I showed in some of the photos, I've made a pair of particles, electron and, sorry, that one's the electron, that one's the positron. That one's losing more energy on it as it travels. You can see from the tighter radius. But here is where your photon came in, so they often use dotted lines to show something was here. In the real life, you just see that suddenly appear in a photo or in an image. So you can work backwards and find out what's going on. Okay, so this is happening all the time. Okay, we need to go back to basics with all of these. So I'm going to finish the kind of the thinking bit and just do a little bit more straightforward factual stuff. They may seem illogical, but all of these reactions have happened by smashing protons together. So the Large Hadron Collider works on smashing protons together. Okay, when they're smashed together, you can make proton and proton and proton and an antiproton. That's fine. Okay, the mathematics of it we'll get into why that's fine, but you could make these pair of protons again and some pions, a positive and a negative. Okay, or you could make neutrons and an anti-neutron. Okay, so there's different ways of doing it, but as long as you've got enough energy, you can make pairs of particles. Notice we've got even numbers at the end. Okay, so that's how we create them. Now, as I've already hinted up there, these aren't really useful units. We tend to use electron volts instead. So all we need to do is keep practicing converting between the two. So again, in your data book, I know we've done it properly, but just remind you, if it all goes to pot in the data book, you actually have it here. So underneath the unified mass constant, okay, mass unit, that many joules is 1 electron volt. Okay, so voltage multiplied by 1.6 times 10 to the minus 19 equals 1.6 times 10 to the minus 19. Okay, so a little bit of practice again. Maybe stop the video here and just get into that practice of doing it after you've put in the numbers. So I'm just going to put in 151 times 10 to the minus 12, etc. from above. And then what does that convert to? Well, by my calculations, I got 938 mega electron volts. And that was for both proton and neutron, as long as it's 3 significant figures or less. Okay, they'll be the same. And then this one, 0.51. So much easier to see the difference, yeah, compared to when you're doing this. So all the questions that I've ever seen will use mega electron volts, but you will need to convert them into joules, if you are using this. Okay, so notice in joules, it's that crucial thing to remember there. Okay, but it's just convenient to add up energy like we did here in mega electron volts. It just makes it so much easier. So again, antiproton, anti-neutron, anti-electron, or I'll just put that in there because we'll use that, or electron plus if you prefer, also perfectly acceptable. Again, it's exactly the same, 938, 938 and 0.51. do fill these tables in. We do have a lot of tables like this in the exam, but it's in this chapter, but it is about that practice of just going, right, well, I could, yeah, that's the same as that one. So we'll end up with lots of figures. It's making sure you're happy to put the right ones in the right place. Okay, so link, a little extra bit. Obviously, this is just the mass, or the energy to create the mass, to create protons, neutrons, and electrons. If you accelerate them as well, then you're gaining an additional energy. Okay, so the total energy of an electron, if you accelerated it by 400 kiloelectron volts, will be, don't forget, that's kilo electron volts, not mega, so that would be 0.4 mega electron volts added. You'd end up with 0.91. Yeah, so if you use 400,000 volts, you'd end up with a much more energy to play with, and that's the basis of particle physics. Radioactivity, you're not accelerating them. When you use accelerators to get into the higher energy stuff, you're just adding on additional energy. And again, because it's scalar, you just add it on. All right, so that gives us much more to play with. So those are all the kind of basic calculation stuff, and two basic principles: pair production and annihilation. I should say, if you are thinking about spelling it, look at it again. Annihilation, so Annie, girl's name, hilation. It kind of works. So yeah, just make sure you're aware of and kind of clear on your head what these two processes are, or these calculations to convert between rest mass energy and rest mass. So mc squared, E equals mc squared, and how to convert them into electron volts, and which things need joules and which things can simply just be added up. Okay, this is a conversion, I should say, but yeah.